So again, integers, counting numbers, 0, the opposites of the counting numbers. And then there's a few ideas of what opposite means. And the basic one is same distance from 0, but on the other side. So the opposite of 3 is -3 because they are each the same distance from 0, but they're on opposite sides. All right, so 3 versus -3 and 0 in the middle forms the idea of an opposite. The other way to think about opposite is what do I add to a number to get 0? That number that I add is the opposite. And it turns out that goes in both directions. So I could make another statement like what plus -3 is equal to 0. And we would eventually come to the conclusion that 3 plus -3 is 0. So just like -3 is the opposite of 3, we can also say that 3 is the opposite of -3. And there's a third way to think about what opposite means. An opposite is the result of multiplying by -1. So for example, if I start with 3, and then I take -1 times 3, I get -3, which is the opposite of 3, which is similarly, if I start with something like -4, and then I multiply that by -1, we've learned in the past that a negative times a negative is a positive. We'll explore that idea some more next class. And 4 is the opposite of -4. So that's another way to think about what it means to be an opposite. And this third way of thinking about an opposite is the way we kind of program computers to think about opposite numbers when we have computers do calculations for us. So we're going to take that and we're going to apply a model to it. So I started thinking about models back here when I was thinking about up versus down, right versus left, to have money and to owe money. And then temperature, positive, negative temperatures, freezing versus not freezing. So those are physical models for what it means to be an integer. Another model based on some toys that we can play with is either the charged particle model or, it's supposed to be an R there, the chip model. Extra P. And they're really very similar, it's just a slightly set of different toys or symbols that we use. So with the charged particle model, we use just a plus symbol and a minus symbol, and a plus symbol is the same as a +1, or just a 1, and the minus symbol is the same as -1. With the chip model, we usually have some colored chips to play with, and sometimes they're plastic, sometimes they're those foam chips, maybe they're wood, there can be a lot of different materials, but we have one side as positive and the other side as negative. So often we'll do something like a red chip will be a 1, and a black or white chip would be a -1. And so we just define that up front. Now, there's a slight problem I have with this model right here, because I can show what +1 looks like, and I could show a number over here like that number right there would represent the number +3, right? Or just 3. Or maybe I would write 3 dash or 5 dashes like this, and I could say, oh yeah, that's the number -5. And similarly over here, I could say, all right, let's show +1, +3. So that would be my 3, looks more like a bowling ball. And then if I use my white or black chips, I could show, hey, there's a set of 5. How do I show a set of 0? Turns out there's 2 ways to show 0. One way to show 0 is just have a set with nothing in it, right? Nothing in it means I have the number 0. Another way to show it with the chip model or the charged particle model is to add a new definition here to our key. So here is my key. And to the key, what I do is I say, if I put a plus and a minus together, oops, wrong direction. If I put a plus and a minus together, they cancel out, and that gives me a 0, right? So this right here would be my key for the charged particle model. So it could be a 0 is nothing. So I have a set with nothing in it. So empty set is one way to talk about 0. But this could be 0 right here with a plus and a minus. Or I could have another plus and a minus because they cancel also. So that's another way to show 0. Over here, similarly, I could have another set here. And in that set, if I put a positive chip and I put a negative chip together, then they represent the idea of 0. So 0 could be nothing, but with these models for integers, we take 2 opposites. The most basic opposite is 1 and -1. We put them together, and that's another way to get 0. So if I extend the key here, for the chip model, I would also have to put in here that if I take a positive and I put it together with a negative, then that's another way to say, hey, that right there is a 0. And I'm just going to put a line through that thing right there to indicate that's a 0, not a chip or a set, so I don't get too confused myself. Now, the interesting thing about either the charged particle model or the chip model, unlike when we're playing with whole numbers, where there's only one way to say, hey, here's a set of 3, 1, 2, 3 things. With the charged particle model, it turns out I can show 3 in different ways. So for example, here, I could also show a set of 3 by having a mixture of positives and negatives, as long as in the end, I net 3 positives. So this set right here is also 3, because this positive and this negative cancel, and this positive and this negative cancel, leaving only positive 3 there. Similarly with the chip model, instead of the charged particle model, I could have a set where I have a whole bunch of blacks in that set. So there's a whole bunch of -1s. And as long as I have just enough positive ones to end up with 3 in the end, I'm okay. So like those 2 could cancel, and 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 those 2 could cancel. At the moment, I have a set of 0. I want a set of 3, so then I just make sure I have an extra 3 of whatever my positive chip looks like. So this set right here is also a representation of the number 3, because I have a bunch of 0s living in here. So that's a new twist on this. And you might say, oh, that's kind of confusing and weird. It is, but it allows us to show some interesting things about how addition and subtraction of signed numbers work, which is what we're going to look at next. So again, I can show 0 in multiple ways. I can show 3 in multiple ways. I can show -3 in, oops, let's see, I got something wrong here. Oh yeah, that's +3. And this right here should be -5. Oops, I know I had a typo here somewhere. -5 there. So let's take a look at addition. Addition. And I'm going to use the charged particle models. I like the pluses and minus symbols. Addition with charged particles. There's 2 things I need to know to do how to do this. 1, what does addition mean? So addition, from way back in the course, we decided means just combine and count. And what am I adding? Well, I'm adding integers here. So the second thing I need to know is what is an integer? An integer is just a set of charged particles, like we saw on the previous page. And so to add integers is just to take some sets of charged particles, combine them and count them and see what happens. So at first, it's pretty straightforward, like 3 plus 4. I have to show a set of 3. 1, 2, 3. I want to combine that with a set of 4. And then put them together, and I get this new set that has 1, 2, 3, 4, 5, 6, 7 of them, right? I have my 4 and my 3 for 7. Positive 7 would be the result. But I can do some things I couldn't do with whole numbers before, because now I have these positive and negative numbers. Suppose I had something like negative 7 plus 4. So in this case, I would have to show negative 7. 1, 2, 3, 4, 5, 6, 7. And I want to combine that. Combine, it's supposed to be an either, with a set of 4. 1, 2, 3, 4. And so I'm going to combine them into this bigger set. And let's list the 7 vertically. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. So there's the combination. Now I have to count them up. And as I count them up, I just want to keep in mind that I just made some zeros here, right? This right here is a 0. This right here is a 0. This right here is a 0. This one right here is a 0. Okay, so we have some zeros here. And after we're done combining, we only have 3 negatives. So the answer has to be negative 3 here, because we have that cancellation, right? That idea with our charged particles, that we have this is our 1, and this is our negative 1. And in addition to nothing being 0, we also have a combination of these things to represent 0. So just like before, combine and count with this extra twist, this idea of opposite charges cancel each other out. So again, this key is usually important when we're trying to deal with these. Let's try another one. Suppose we had 5 plus negative 3. I'm modeling addition here. A lot of times we look at that in our head because of our experience. We think of a subtraction. Oh, that's like 5 minus 3. Maybe, but right now it's 5 plus negative 3. And that's what I want to show. So here would be my 5. And I want to combine that with my 3. Or negative 3, excuse me. And often when I combine them, I like to line them up. It doesn't really matter which way you go. So I'm going to combine them. I could make the 5 go like this, horizontally in a row. And have a row for negative 3 underneath. And again, when I consider this, I've just made a bunch of zeros. I've made 1, 2, 3 zeros. And so that means the net charge here, the net result of combining is just 2, positive 2 is what I end up with. Now, it is an interesting coincidence here. Oops. That 5 minus 3 is also equal to 2. Right? And we'll pick on that coincidence more and more as we see it. So that's something kind of cool to point out. Kids will notice that, and we're like, yeah, that's cool. Look at that. Huh, does that happen often? Let's try it again. So then we pick another one. And again, these models are for getting the idea of what it means to add these signed numbers, these integers. Once we get bigger numbers, we need an algorithm. We don't want to draw these pictures all the time, but we want to get this number sense in our heads, this kind of geometry of why do these things work the way they do. So suppose I had 7 plus -3. We would draw our 7. So there's my set of 7. And I want to combine that with my set of 3, -3. And I put them together in some way. So there's my 7, and then maybe I'll put my 3 right there. And I've got a bunch of zeros here, and I can see that that leaves 4. And I can note, hey, this is like 7 minus 3. That's also 4. Okay. Now, it's not always like a subtraction problem. We saw a previous example of that. Sometimes it's a little deeper than that. Sometimes it's a little backwards from that. Like on the previous page, we had -7 plus 4 is -3. There's kind of a subtraction going on, right? 7 minus 4 is +3, but this one ended up being negative. So interesting, but weird. Not quite, but almost like 7 minus 4, which is +3, but we got -3 there. So there's kind of a connection some kids will see there, and we'll come back to that. And then another example is, what if we had something like 3 plus -7? So we could have our 3 that we combine with the -7. And that gives us a new set. Seven negatives, 3 positives, and I can see I kind of lined them up so I can see a few zeros there, and I get -4 as the answer. And again, kids were used to whole numbers where the answer was a whole number, but now, is this like 3 minus 7, which we haven't seen before? Well, let's see. I know, so question mark, I know that 7 minus 3 is 4. Now I'm reversing that. So if we think about maybe money, this would be like a gain and a loss. I gained $7, but then I lost 3. I gained $7 and maybe I spent 3. That leaves me with 4. On the other hand, if I had $3 and I spent 7, whoa, wait a minute, you're trying to spend more than you have? Well, that's the idea of debt. You owe me now, if that's what you want to do, -4, oops, 4 there. Okay, so there is this relationship between addition and subtraction that kids have seen before in a different way. This is a new way. Before we had fact families to look at that, but now we're in the realm of similar problems, but with negatives. So it's not quite a fact family, they're related but different. So next we need to look at subtraction of whole numbers.